Hello, everyone. My name is Shahim. At first, let's talk about this course, Embedded Linux, and see what we're expecting to see in here. What I'm thinking about this course is that first we will learn about the Yocto project, how to compile the kernel from scratch for our own desired board. Then we will learn how to write a Linux kernel driver. My future vision is that somehow add some machine learning to the embedded design, but it is far ahead from now. Let's just see how everything will go. In the first lecture, we will learn about the Yocto project. Then we will compile a kernel for our board. I'm just thinking to compile the Linux for one of the NXP SoC families, probably IMX 233. And because there is a good header board from the Olimex for that board. After that, we will see how the partition will be look like for booting up a Linux. And finally, we'll look at the booting process. What is the U-boot, what is the first stage bootloader, what is the second stage bootloader, and so on. Let's start with the first lecture. When the hardware guy designed the SoC board, it's time to compile the Linux kernel for their specific demands, because all the components available in the board should be known by the kernel. On top of that, each SoC required some configuration in its kernel. For example, when you add an audio decoder IC, which is connected to the SoC, say using an I2S interface, so the kernel should know that, how to deal with that IC, how to communicate with that. So there should be some packages and modules should be installed on the kernel to do that. Or for example, when you connect the Wi-Fi USB dongle to the board, so the kernel automatically detect the package, detect the modules, and run the desired driver for that. Each SoC needs some configuration in the kernel to deal with some internal interfaces. For example, HDMI, for example, LVDS output. So each of them are different from SoC to SoC. For example, the NXP or Rockchip or Allwinner has different configuration for these internal interfaces. So we have to build the kernel from the scratch in order to be able kernel understand this configuration for our own board and our own SoC. The good thing about Yocto is that, for example, when you are trying to change one of these packages, one of these recipes, there's no need to just rebuild the whole thing from the scratch. Instead, the Yocto just rebuild the only necessary packages and its dependency. So let's have a quick start with the Yocto project. If you go to the Yocto website, you will find lots of good information and good documentation there. So in a general view, Yocto project is a set of tools to build and validate the kernels for your specific demands. The Yocto has two main components, the Pocky and BitBake. And you can see the Open Embedded on here. If you came from the ancient time, you probably heard about the Open Embedded as a separate project. But over the time, because Yocto project and Open Embedded was working on the same team, they merged together and under an umbrella name of Yocto. So let's have some, describe some common terms. The first one is the metadata. So as you can see here, the Pocky consists of metadata. So metadata is directories and informations that tell Yocto and BitBake how to build the kernel. In that case, we have configuration files. You will find them by .conf format. So .conf format basically have global variable and definition stores them. We have recipes. Recipes basically came with the format .bb, .bb class, or bb append. Those files will contain a list of setting and instruction for building the package. So a collection of the recipes we call layer, and a collection of the layer which is known as a Pocky in here. So what is the bitbake? Bitbake is the build engine, is the core part of the whole project. Keeping that in mind, these two terms, let's just highlight them. And a scheduler and execution engine. So what bitbake is actually doing, so when we call bitbake, bitbake will go through all these meta files, read all these configuration files, read all these recipes, and based on the information on these recipes, execute some task. For example, in one of these recipes, it asks, for example, install some packages, download some packages, and then configure it, and then build it for our kernel. So everything will be run under the bitbake. So we have another term, you will might hear it most often, BSP, board support package. So basically, BSP is a set of layers that enable support for a specific hardware. For example, BeagleBone Black has a board support package. The designer of the board provides some layers that say that, okay, our board have some special IC, and this IC has needs some packages to communicate with. So if you're a embedded designer designing some board for your companies, so you have to provide some BSP packages for them. You have to collect some layers that say that what kind of IC, what kind of packages that you need for this hardware. So the next step is that just let's start and go to the Yocto Project website. So when you go to the Yocto Project website, under the software, you can download the whole project. So the latest release is the Onister 3.4. So it's a good time to see the history version of the Yocto. When you go to the wiki page and release, you will see that each version of the Yocto project has a code name. For example, in our case, version 3.5 known as a Kirkstone, or version 3.4 named as a Onister. So the Kirkstone is not actually released right now, but it has the LTS support, long time support. Onister is the current branch that they are working on. It just has only support for 7 months, but if you are working in the big companies, they are actually interested to go for some LTS packages and LTS software. So Donfil is a version 3.1, has the LTS support. So this is also my favorite. And we will download this version 3.1. Back to the download page. Okay, download page. You will click on here and then select the correct version. So the branch will change to the Donfil. We just copy that. And basically, you have to have the Ubuntu, or Linux host OS in order to run the Yocto project. So open up a new terminal, CD desktop. I basically create a new directory in here, say Pocky_1, CD Pocky_1, and just copy and paste that line. Hit the enter. It just take a moment to clone the repository on your folder. If I go in here, so Pocky, it's not yet here. Wait a second. Okay, before going forward. So in order to install and work with the Yocto project, you need some packages to be installed on your host system. So you can go to the document, the main website under document, and then document overview, quick build. So go a little bit down, host packages. So you have to have all these packages on your host system, in my case, Ubuntu, in order to be able to run the Bitbake. I just copy all these lines and then come back to the Ubuntu host system and also install all these packages. Hit the enter, my password. I already had all these packages, so it doesn't take too much. Just say that, okay, all of them are already installed in my computer. But you might, for your situation, might take a little bit. So this is the Pocky Yocto project that we just cloned. So as you can see here, we have a Bitbake core, we have documentation, and we have lots of metadata, as you can see on here. Meta Pocky, meta self-test, meta skeleton, and meta Yocto BSP. So what we are gonna do is that we can just go to one of these, we call these layers. We can go to one of these layers and you can see that it has classes, conf file, and recipes. When we go to the conf, did you remember we said that some file that has the format.conf, and these files are have some global variable and some global definition to, and under recipes, everything that comes with the .bb recipe and bb append, these are our recipes. Go and compile them and run them. After that, we have recipe cores. So you can see that on here, for example, we have 3 recipes, 3 subcategories. We go to, for example, one of them, tiny init, and we will see one of the recipes on here. Open up one of the recipes. So there are some basic information about summary, description, what is this recipe is about, basic initialization system for Pocky Tiny. So we have R dependence, we have a source file. So source file, source URL, which it tells the Bitbake, go to this address and download all the files for us. For example, in our case, all of them are local files. So in that case, init, go to the file init. So go to the file and see the init file. Just load them, fetch them, and do whatever you want with them. So as we told earlier, under the recipes, we said that how the Bitbake should install and run each package. So under the do configure, so after the downloading, you have to configure the file. Every line on here will be performed. For the compilation of the package, you have to perform this line. In our case, we don't have anything. And for the installation, you have Bitbake will run these lines one by one. We can also go to another recipe. For example, if I go to the meta file, meta layer, and then go to the multimedia recipe, and then go to the lib PNG, for example. This is one of the packages that should be installed on the kernel. We can open up this libpng, this version. So PNG image format decoder library. So the bitbake will install these packages. So the kernel will be able to just decode some PNG files, description, we have a license, we have a dependency, for example, dependency is here. So this package, libpng, is dependent on the zlib package. Did you remember on the bitbake, on the Word file that I have shown you, bitbake is a scheduler, and let's go back on here. Bitbake is a scheduler and execution engine. So a scheduler means that, for example, bitbake won't install libpng until it satisfies this library first. So a scheduler means that bitbake will install zlib library. After that, it will install libpng library or package. For example, we have a source URI. So you can see that it will download the file from this URL and some checksum, make sure that the downloaded file has doesn't miss any bytes. And then, yeah, that's enough for this package. So we can start with some example on here. Open up a terminal under the POKey, open terminal. So actually we are in the POKey directory, and print source OE init build environment. As soon as I hit the enter, some file will be created for us, the build directory. Let's start with the build directory. When you go to the build directory under the conf, you have two configuration files. Remember that conf file stores some global variable and some definition that bitbake can go through that and build your project. Go to the bblayers.conf. So bblayers said that which layers should be included for the compiling the kernel. For example, in that case, bitbake read all these meta layers, metadata or layers, and then go through them, read all the recipes, and schedule them, and then try to compile all of the recipes in these directories one by one. Then we have a local conf. So inside the local conf, we have to specify which machine or which target we are interested to compile the kernel for. Kernel should be installed for this package, I mean for this target. We can just say x86. So this is one of the targets machines. So QEMU is a kind of emulator. Instead of just compiling, I mean, instead of running this kernel on the SoC, for example, we can compile it for an emulator and then see how everything is working on the simulation. Then we have DL directory. So DL directory basically shows you where all the file and packages should be downloaded to. We have a SSH directory. When we download the files and then when we compile them, they will be stored in a SSH directory. So for the later time, when you compile the kernel for another target, there's no need to download, and then there's no need to compile all packages from the scratch. Instead, it will look at the SSH cache and see if they are already there. So it just saved lots of time for you. We have a temp directory. Let's see what we have in here. recipe, and then we have, let's see what we have on here. I mean, for the first case, there is no need to change many things in this conf file, unless the very first one, the machine. But later on, when we are using the IMX board, we have to change the target machine to the IMX board and change some of the configuration on the local conf file. What you have to do is that call bitbake fbase, and the target should be one of these: core image minimal, core image sato. The Yocto also have a very good documentation on this topic. If you go to this web page for building the images, you have some targets. Core image based, which means that the kernel will be installed with the console only, and full support to the target device hardware. So we have another one, for example, image-based minimal. Okay, where is that, the minimal? And then we have a core image minimal, a small image just capable of allowing a device to boot. So in our case, we can just go for a core image base. And then core dash image dash base, hit enter. So we have a parsing recipe. As you have seen that we have multiple layers, and each layer has several recipes. So first, bitbake goes to the recipes, parse them, and see which recipe should be run before another. So as you remember, some of the recipes are dependent on another recipes. So in our case, parsing just make sure that all the tasks will be in the correct format. It takes a few moments to complete. So bitbake is reading all the recipes one by one, parse them, which one should be run first. Okay. And then it will initialize the task. Which task should be run first? So right now, as you can see here, there are almost 4,000 tasks should be executed to compile the kernel for our desired target. And as you can see, 6 tasks or 8 tasks will be run at the same time. So it just saves lots of time for you. So you can see that some of them are do fetch, which means that the bitbake just going to the source URI and downloading the source file. Some of them are do configure, which means that after the fetching and downloading the files, it will configure them, make them ready to install. Some of them going to the do patch, do unpack. So basically some of the packages will be downloaded on the compressed format. They will just unpack them. And these are the package name, glibc. This is the version, Python 2, OpenSSL is downloading, OpenSSL is patching. This is a really time-consuming process. If you are doing it for the very first time, it might take, I don't know, 4 or 5 hours. Depends on the host system that you are working on. I'm just using on the VMware, but you can just have install the Ubuntu from using the hard drive, so it's much faster. So this process will be this process might take shorter for you. Do compile, for example, we have do compile. So it is actually compiling the OpenSSL native version 1.1. I'm not going through that because I already have installed everything. In my case, I can just go back to my main folder. Just let me delete this Pocky one. Okay, this is my main Pocky. Open a terminal. Similar as before, source, OE, init. Let's see what is our configuration look like under the bit, under the build folder, under the conf. For example, local conf. So this is my main machines. So as soon as I just call the bit bake core dash image dash base, hit enter. It actually loading my cache because I already have lots of packages installed in my computer. So there's no need to just download them again. So you just fetch them from my SS state file. Just doing some tasks, make sure everything is okay. What you can do is that in your local conf file, you can add number of threads, for example, and parallel make. For example, in our case, I said that I have 8 threads in my CPU, and BitBake will be able to run 8 tasks at a time. So just add these 2 lines at the end of your local conf. So it will make you to run multiple tasks at the same time. Okay, it's going too fast. Okay, come on. Let's see what will happen. Okay, it's done. And as you can see on the build directory, you have several new directory created for you. You have to go for a temp and then deploy images. And in the later video for the IMX board, when we are compiling the kernel for the SOC, we will teach you how to use these rootfs file and uboot files to run on the real embedded system. But here we have a Q emulator. So Q emulator is basically a simulator for running the embedded system. Emulator for running the embedded Linux in the host computer. So you have to say run QEMU and then say the target. So our target was QEMUX86. Hit the run button and emulator will run and load all these rootfs file and uboot files and run the kernel for you. Okay, this is your first build kernel system. It actually running the kernel. Let's see. And after a moment, you will see that the kernel will pop up. And okay, right now we're in the login part. The root operating system. We can use ls, we can use pwd, whatever. You can use uname-a to see what is our Linux version. So right now we are running the kernel 5.4, and that's everything that you have to do for the And that's everything you need for compiling the kernel. In the next video, we will teach you how to compile the kernel for the IMX233 board.